Far beyond the reaches of our solar system, deep in the ink-black void of space, an ancient star breathes its last. And in doing so, it doesn't fade gently into the night. It erupts. A blinding flash, brighter than billions of suns, tears through the galaxy. In a matter of seconds, the star that burned for millions, perhaps billions, of years dies in a display so powerful that it alters the chemistry of the cosmos. This is a supernova, a cosmic super-event, a violent, brilliant, and ultimately beautiful ending. But it's not just a death, it's a beginning, because in that explosion, something miraculous happens. Atoms are born, matter is scattered, and the seeds of future stars and future life are sown. A supernova is the universe's way of recycling, taking what once was, breaking it apart, and building something new. In every sense, it's a transformation, one that affects galaxies, planets, and even you. To understand a supernova, we must first understand the star itself. Stars are not static. They live, they evolve, they struggle in a delicate balance between gravity and fusion. Gravity tries to pull the star inward, crushing it into itself. But deep in the core, nuclear fusion pushes outward, generating light, heat, and pressure. This tug-of-war continues for most of a star's life. But it's only temporary. Over time, hydrogen, the star's main fuel, runs low. So the star begins fusing heavier elements, one layer after another. Helium becomes carbon. Carbon becomes oxygen. Oxygen becomes silicon. And finally, iron. But iron is different. It doesn't release energy through fusion, it consumes it. Once iron dominates the core, fusion halts, and gravity wins. In seconds, the core collapses. The outer layers crash inward, rebound violently, and explode outward with ferocity beyond comprehension. That is the moment of the supernova. And in that instant, the star is no longer what it was. It becomes something else, a nebula, a neutron star, a black hole, and the builder of future worlds. Not all supernovae are created the same. There are two main types, and their differences tell two very different stories. The first is a core collapse supernova, triggered when a massive star, typically 8 or more times the mass of our Sun, runs out of fuel and can no longer support its own weight. The result is a violent implosion, followed by an explosion. The second is a Type I supernova, quieter in its buildup, but no less dramatic. It begins with a white dwarf, a remnant of a smaller star, siphoning material from a neighboring star. When it gathers too much mass, it ignites in a thermonuclear blaze, destroying itself in a flash of near-perfect brightness. Type I supernovae are special. Their consistent luminosity makes them reliable standard candles, tools for measuring the vast distances of the universe. By studying them, astronomers discovered something astonishing, that the universe is not only expanding, it's accelerating. This expansion points to something mysterious, something we call dark energy, and we only know it exists because of dying stars. The light from a supernova can travel for millions, even billions of years before it reaches us. It is a time capsule, information frozen in motion, only now arriving. When we look through our telescopes and witness the flare of a supernova in a distant galaxy, we're not seeing something that's happening now. We're watching a celestial obituary from eons ago. The universe is so vast, so ancient, that even its most immediate events are delivered to us on delay. And yet, they speak to us clearly. The light reveals the composition of the star. The shockwaves tell us how galaxies evolve. The expanding remnants give us clues about matter, time, and the physics of existence itself. Every supernova we see is a story, written in light, scattered across the cosmos, and waiting to be read. In the heart of a star, simple atoms are forged into complex elements. But the heaviest, most precious materials, gold, uranium, platinum, lead, are born only in the intense crucible of a supernova. Without supernovae, the universe would be hydrogen, helium, and not much else. There would be no iron in our blood, no oxygen in the air, no carbon in our cells. The periodic table of elements is not just a catalog of matter. It's a biography of the universe, and its chapters are written by stars, ending in supernovae. Even the atoms in the device you're using now, the lithium in your battery, the silicon in your screen, were forged in ancient stellar furnaces and delivered to this solar system by titanic explosions long before Earth formed. You are not just connected to the stars, you are made of them. When a star dies, it doesn't always disappear entirely. Sometimes, it leaves behind a core so dense, so strange, that the laws of physics seem to bend around it. If the collapsed core is massive but not extreme, it forms a neutron star, a dense sphere, only a few kilometers wide, but heavier than our Sun. A thimble of neutron star material would outweigh Mount Everest. Some of these spin rapidly, emitting beams of radiation from their magnetic poles. When these beams sweep past Earth, we detect regular pulses, hence the name, pulsars. But if the star is truly massive, something more mysterious happens. It becomes a black hole, a region of space-time so warped that not even light can escape. Invisible, intense, implacable, born from destruction, they become the quiet engines of galaxies. Supernovae are not just fireworks. They are sculptors. Each explosion sends shock waves through the interstellar medium, compressing gas clouds, triggering new waves of star formation, and injecting energy into the galactic environment. They regulate the birth and death of stars. They prevent the buildup of too much gas. They shape the spiral arms and glowing halos of galaxies. Without supernovae, galaxies would be colder, quieter, less dynamic. They are not just events. They are architects. Even long after the light fades, the remnants of a supernova continue to shape the cosmos. The Crab Nebula, the glowing remains of the 1054 supernova, still expands today, nearly 1,000 years after it exploded. Telescopes see its filaments twisting through space, glowing with synchrotron radiation, pulsing with the rhythm of a neutron star at its core. In that cloud are atoms still drifting, still finding their place, still becoming part of the next generation of stars. This is the universe's way. It never lets go. It reuses. It recycles. It continues. In every corner of the sky, there are the ghosts of supernovae. Some we see clearly, brilliant explosions frozen in Hubble's lens. Others are hidden in X-rays or radio waves, or gravitational ripples we are just now learning to detect. They are everywhere, and they are ancient. Yet, in their patterns, in their structures, we see a kind of order, a rhythm, a plan. The universe is not random chaos. It is a process of birth, life, death, and renewal. And supernovae are at its heart. In the end, every star must die. But in that death, something astonishing happens. The universe reclaims its material. It sends it outward. It stirs the pot of creation once again. Nothing is wasted. Nothing is truly lost. We are here, on this small, blue world, because long ago, stars lived and died, exploded and scattered their dust into the void. That dust formed our sun, our planet, our bodies. Every heartbeat is a gift from a star that once exploded. Every breath carries atoms that traveled through supernova winds. You are not apart from the universe. You are its recycled light.